get some work done. So we finished chapter 13, so mark that as done. Alright. Yeah, let's continue reading. File systems. One thing that I just realized is that I've been misspelling file systems because I was looking at the description of the stream and I spell it all as one word. And I did that in the README here as well. But it's actually two words. File systems. I don't know why I just thought of it as one word. Anyways, let's continue reading. A file system is an organized collection of regular files and directories. A file system is created using the makefs command. One of the strengths of Linux is that it supports a wide variety of file systems, including the following: the traditional ext2, 3, and 4 file system, various native Unix file systems such as the Minix, systemv, and BSD file systems, Linux FAT, FAT32, and NTFS file systems, the ISO 9660 CD-ROM file system, Apple Macintosh HFS, a range of network file systems including Suns, widely used NFS. Information about the Linux implementation of NFS is available at so-and-so. IBM and Microsoft's SMB, server message block, I think it is. Novell's NCP, and the Coda file system developed at Carnegie Mellon University, and a range of journaling file systems including ext3, 4, RiserFS, JFS, XFS, and BTRFS. The file system types currently known by the kernel can be viewed in the Linux-specific proc file systems. Okay. Them up proc file systems. Huh. BPF file system. Interesting. I'm guessing these are more like virtual file systems. And then we have ext234, file system user space, fuse, block, BTRFS, VFAT, ISO, overlay. So these Node V seem more like virtual file systems, whereas these are more like hard drive file systems, or CD-ROM in this case, or I guess that can be like little jump drives and stuff like that. Let's see, I'm gonna refresh my chat here. I've been missing some of the chats just because I don't look at the chat usually while I'm streaming. But yeah, I'll try to get better at that. Alright. Let's see here. Linux 2614 added the file system user space fuse facility, a mechanism that adds hooks to the kernel that allow a file system to be completely implemented via a user space program without needing to patch or recompile the kernel. For further details, see fuse sourceforge.net. The ext2 file system, for many years, the most widely used file system on Linux was ext2. The second, extended file system, which is a successor to the original Linux file system, ext. In more recent times, the use of ext2 has declined in favor of various journaling file systems. Sometimes it's useful to describe generic file system concepts in terms of a specific file system implementation. And for this purpose, we use the ext2 as an example at various points later in the chapter. The ext2 file system was written by Remy Card. The source code for ext2 is small, around 5,000 lines of C. It forms the model for several other file systems implementations. The ext2 homepage. The website includes a good overview paper describing the implementation of ext2. The Linux kernel, an online book by David Russling, available at so-and-so, also describes ext2. The file system structure. The basic unit for allocating space on the file system is a logical block, which is some multiple of continuous physical blocks on the device, this device on which the file system resides. For example, the logical block size on ext2 is 1024, 2048, or 4096 bytes. The logical block size is specified as an argument to the makefs command used to build the file system. A privileged capsys raw IO program can use the fib map ioctl operation to determine the physical location of a specified block of a file. The third argument to the call is a value result integer. Before the call, the argument should be set to a logical block number. The first logical block is number 0. After the call, it is set to a number of starting physical block where that logical block is stored. Before the call, the argument should be set to a logical block number. After the call, it is set to the number. Okay, that makes sense. Figure 14.1 shows the relationship between disk partitions and file systems, and shows the parts of a generic file system. So you have disk, partition, partition, partition. Inside one partition, you have boot block, which I think this is for MBR, master boot record partitioning, versus the more modern, what do they call it? GUID? Is it GUID? Let's ask AI. I'm somewhat familiar with MBR partitions. Can you explain, or what are the modern alternatives? I think it's called GUID. GPT, GUID partition table, yeah. +128 partitions. I wonder who developed it. Part of the UEFI boot standard. Apple partition map, older Macs. Yeah. Linux Volume Manager, LVM, not exactly a partition table, but extracts storage into volumes over partitions. Flexible resizing, snapshot, combining disk, yeah. ZFS pools, again, not just partitions. ZFS handles disk layout, internally, RAID. Yeah. Who developed the GUID? They chose Microsoft. Originated from Intel in the late 90s. Okay, that's good to know. Yeah, so the boot block block thing, I think that's done away with. But I'm not sure. File system boot block, super block, inode, table, data blocks. The file system contains the following parts. Boot block. This is always the first block in the file system. The boot block is not used by the file system, rather it contains information used to boot the operating system. Although only one boot block is needed by the operating system, all file systems have a boot block, most of which are unused. Let's go back to AI. Back to here. Do file systems in GPT partitions use boot blocks? Yes, but tens of the file systems in the boot process. GPT itself is just a partitioning scheme, so whether there's a boot block is determined by the file system and bootloader. Not GPT directly. MBR versus GPT boot area. MBR, the very first sector, LBA 0, is the master boot record, which contains both a small bootloader and the partition table. File systems inside MBR partitions may also have their own boot sectors. GPT, LBA 0, it still has a protective MBR to stop old MBR tools from overwriting the disk. LBA 1 is the end of disk store primary and backup GPT header/tables. GPT itself does not include a bootloader. Most file systems still have a boot block or super block, but it's file system specific. Bootloader grub may embed code in the first sectors. First sector of partition. BIOS. Okay. The boot block. Super block. This is a single block immediately following the boot block, which contains parameter information about the file system, including the size of the inode table, the size of logical blocks in the file system, and the size of the file system in logical blocks. Different file systems residing on the same physical drive can be of different types and sizes and have different parameter settings, e.g. block size. This is one of the reasons for splitting a disk into multiple partitions. inode table. Each file or directory in the file system has a unique entry in the inode table. Each file directory, yeah, okay, that makes sense. This entry records various information about the file. Inodes are discussed in greater detail in the next section. The inode table is sometimes also called the ilist. Data blocks. The great majority of space in the file system is used for blocks of data that form the files and directories residing in the file system. In the specified case of ext2 file systems, the picture is somewhat more complex than described in the main text. After the initial boot block, the file system is broken into a set of equally sized block groups. Each block group contains a copy of the super block, parameter information about the block group, and then the inode table and data blocks for this block group. By attempting to store all of the blocks of a file within the same block group, the ext2 file system aims to reduce seek time when sequentially accessing files. For further information, see the Linux source code. So-and-so, the source code of the dump-e2fs program that comes as part of the e2fs progs package. Okay. Oh, sorry, I got this up still. Yay, now we're going to talk about inodes. The file system inode table contains one inode, search for index node, for each file residing in the file system. The inodes are identified numerically by their sequential location in the inode table. The inode number, or simply inumber, is a file is the first field displayed by the ls-li command. Ooh, interesting. Let's try running that on maybe, yeah, let's do ls-li. Yeah, there it is. If we do ls-li on proc, it's a virtual file system. There should be no inodes, right? All right, wrong. Are these the same numbers here? No, they're different. So even proc has inode, concept of inodes. Okay. The information maintained in an inode includes the following: file type, regular file, directory, symbolic link, character, device, owner, group, access. So okay, 3 timestamps time. 3 timestamps time of last access of file, time of last modification of file, and time of last status change. Last change to inode information. As on other Unix implementations, it is notable that most Linux file systems don't record the creation time of a file. Really? I thought that was like something that Mac FS, Apple file systems do. Let's ask AI. Does Apple file system record a file creation time in the inode? APFS does not store file creation time. Wait a minute. Does not store file creation time. Creation time. Just do like stat on build.zig. Access, modify, change, birth. There is a birth here. Wait a minute. Birth is after the modify? Well, we'll just touch, or we'll say echo foo into test. And then we'll vim test, or vim test, add bar. And then touch test. And then stat test. Okay, there is a birth time. I guess it's not in the inode table. Yeah. Okay, so this is an outdated part of the book, I guess. Number of hard links to the file. Size of the file in bytes. Number of blocks actually allocated to the file, measured in units of 512 byte blocks. Okay. Number of blocks actually allocated to the file measured in units of 512 byte blocks. There may not be a simple correspondence between this number and the size of the file in bytes, since the file can contain holes and thus require fewer allocated blocks than would be expected during this nominal size in bytes. Pointers to the data blocks of the file. Inodes and data blocks pointers in ext2. Let's get through this. Like most Unix systems, the ext2 file system doesn't store the data blocks of a file contiguously or even in sequential order, though it does attempt to store them close to one another. To locate the file data blocks, the kernel maintains a set of pointers in the inode. The system used for doing this on the ext2 file system is shown in figure 14.2, which is the next page over. Let's take a look at that. So we got the inode entry, all the data for the inode, and then we have pointers to the data blocks. And then there's indirect pointer blocks, indirect pointer blocks. Yeah, that's what it's called. Okay. Let's go back. Removing the need to store the block of a file contiguously allows the file system to use space in an efficient way. In particular, it reduces the incident of fragmentation. Of free disk space, the wastage created by the existence of numerous pieces of non-contiguous free space, all of which are too small to use. Put conversely, we could say that the advantage of efficiently using the free disk space is paid for by fragmenting files in the filled disk space. Under ext2, let's actually go back over to here. In modern file systems, is defragment of the file system useful? I need to stop doing that. Fragmenting. Many modern file systems are designed to avoid fragmentation in the first place. Windows NTFS uses Free Space Manager to reduce fragmentation. Small to medium files are usually stored contiguously. Linux ext4 allocates blocks intelligently and tries to keep related blocks together. ext4 also has delayed allocation, which improves contiguity. XFS, BTRFS, ZFS, these are advanced file systems that allocate large contiguous chunks and are very resistant to fragmentation. APFS uses copy on write and space sharing to prevent fragmentation. when defragmentation might help on hard drives. If the disk is very full and fragmented, you may have very large files that are heavily fragmented. On older systems, fragmentation could noticeably slow things down. SSDs, defragmentation is not useful. Can actually reduce the lifespan of the drive because SSDs have a limited number of write cycles. SSDs can't access all blocks at the same speed, so fragmentation does not impact performance. Modern file systems on Linux rarely need manual defragmentation. ZFS and PTRFS even have built-in mechanisms like block allocation and copy run write that make manual defragmentation unnecessary. Makes sense. Okay. Under ext2, each inode contains 15 pointers. The first 12 of these pointers, numbers 0 to 11, in figure 4. Figure 14.2 point to a location of the file system of the first 12 blocks of the file. The next pointer is a pointer to a block of pointers that give location of the 13th and subsequent data blocks of the file. The number of pointers in this block depends on the block size of the system. Each pointer requires 4 bytes. There may be, sorry. Each pointer requires 4 bytes, so there may be from 256 pointers for a 1024 byte block size to 1024 pointers for a 4096 block size. This allows for quite large files. For even larger files, the 14th pointer, number 13 in the diagram, is a double indirect pointer. It points to blocks of pointers that in turn point to blocks of pointers that in turn point to data blocks of the file. It should be needed for truly enormous file for a truly enormous file, and should the need for a truly enormous file arise, there is a further level in direction. The last pointer in the inode is a triple indirect pointer. This seemingly complex system is designed to satisfy a number of requirements. To begin with, it allows the inode structure to be a fixed size, while at the same time allowing for files of arbitrary size. Additionally, it allows the file system to store the blocks of the files non-contiguously, while also allowing the data to be accessed randomly via lseek. The kernel just needs to calculate which pointers to follow. Finally, for small files, which form the overwhelming majority of files on both systems, this scheme allows the file data blocks to be accessed rapidly via the direct pointers of the inode. Structure of file blocks for a file in the ext2 file system. As an example, the author measured one system containing somewhat more than 150,000 files. Just over 30% of the files were less than 100 bytes in size, and 80% occupied 10,000 bytes or less. Assuming a 1024 byte block size, all of the latter files could be referenced using just 12 direct pointers, which can refer to blocks containing a total of 12,288 bytes. Using a 4096 byte block size, this limit rises to 49,152 bytes. 90% of the files of the system fall under the limit. This design also allows for enormous file sizes. For a block size of 4096 bytes, the theoretical largest file size is slightly more than 1024 times 1024 times 1024 times 4096, or approximately 4 terabytes. 4096 gigabytes. Let's see. We say slightly more because of the blocks pointed to by the direct, indirect, and double indirect pointers. These are insignificant compared to the range that can be pointed to by the triple indirect pointer. Boom. One other benefit conferred by this design is that files can have holes, as described in section 4.7, rather than allocate blocks of null bytes for the holes in the file. The file system can just mark with a value of 0 appropriate pointers in the inode and in the indirect pointer blocks that indicate that they don't refer to actual disk blocks. The virtual file system, VFS. Each of the file systems available in Linux differs in the details of its implementation. Such differences include, for example, the way in which the blocks of the file are allocated and the manner in which the directories are organized. If every program that worked with files needed to understand the specific details of each file system, the task of writing programs that worked with all the different file systems would be nearly impossible. The virtual file system, VFS, sometimes also referred to as the virtual file switch, is a kernel feature that resolves this problem by creating an abstraction layer for file system operations. The idea behind the VFS is straightforward. The VFS defines a generic interface for file system operations. All programs that work with files specify their operations in terms of this generic interface. Each file system provides an implementation of the VFS interface. Under this scheme, programs need to understand only the VFS interface and can ignore details of individual file system implementations. The VFS interface includes operations operations corresponding to all of the usual system calls for working with file systems and directories, such as open, read, write, lseek, close, truncate, stat, mount, unmount, nmap, makedir, link, unlink, symlink, and rename. The VFS abstraction layer is closely modeled on the traditional Unix file system model. Naturally, some file systems, especially non-Unix file systems, don't support all of VFS operations. E.g., Microsoft's VFAT doesn't support the notion of symbolic links created using symlink. In such cases, the underlying file system passes an error code back to the VFS layer indicating the lack of support, and the VFS in turn passes the error code back to the application. I mean, does that mean the VFS is just a subset of the Linux syscall table? Because there isn't really like a thing the application is interacting with other than those syscalls. Journaling file systems. The x2 file system is a good example of a traditional Unix file system and suffers from a classic limitation of such file systems. After a system crash, a file system consistency check must be performed on reboot in order to ensure integrity of the file system. This is necessary because at the time of the system crash, a file update may have been only partially completed, and the file system metadata, directory entries, inode information, and file data block pointers may be in an inconsistent state, so that the file system might be further damaged if these inconsistencies are not repaired. A file system consistency check ensures the consistency of the file system metadata. Where possible, repairs are performed, otherwise information that is not retrievable, possibly including file data, is discarded. The problem is that consistency check requires examining the entire file system. On a small file system, this may take on a small file system, this may take anything from several seconds to a few minutes. On large file systems, it may require several hours, which is a serious problem for systems that must maintain high availability, e.g. network servers. Journaling file systems eliminate the need for lengthy file system consistency checks after a system crash. Journaling file system logs, journals, all metadata updates to a specific on-disk journal file before they are actually carried out. The updates are logged in groups of related metadata updates, transactions. In the event of a system crash in the middle of a transaction on system reboot, the log can be used to rapidly redo any incomplete updates and bring the file system back to a consistent state. To borrow database parlance, we can say that a journaling file system ensures that the file metadata transactions are always committed to as a complete unit. Even very large journaling file systems can typically be available within seconds after a system crash, making them very attractive for systems with high availability requirements. I wonder why databases still use file systems, because it seems like they must be reinventing a lot of this stuff. Maybe for compatibility. Like, I'd imagine, like, wouldn't it be a better interface for a database if you just gave it the raw block device and just said, hey, have at it. There's no file system on there. You can just do whatever you want with these blocks. allow it to manage everything outside of the file system. Maybe there's some benefit I'm unaware of. Anyways, the most notable disadvantage of journaling is that it adds time to file updates. Though a good design can make this overhead low. Some journaling file systems ensure that only consistency of file metadata, because they don't log file data, data may still be lost in the event of a crash. The XT3, 4, and RiserFS file system provide options for logging data updates, but depending on the workload, this may result in lower file I/O performance, obviously. The journaling file system available for Linux include the following. RiserFS was the first of the journaling file systems to be integrated into the kernel. RiserFS provides a feature called tail packing or tail merging small files, and the final fragment of larger files are packed into same disk blocks as the file metadata. Because many systems have and some applications create large numbers of small files, this can save a significant amount of disk space. The XT3, so I think RiserFS was removed from the kernel, right? I mean, obviously it's not listed in my proc file systems file, so I don't think it was there. Let's cat out proc file systems grep I riser R-E-I-S-E-R. Yeah. Yeah. I think it was removed because like the wasn't like the creator like arrested for something? Let's ask AI. What is the deal with the creator of RiserFS? And is it still in the kernel? Yeah, he was arrested and convicted for the murder of his estranged wife. And then it was removed from the kernel. (2022). So that's somewhat recent, about a year ago. Hans Reiser. Yeah, that's what I thought. Alright. The XT3 file system was a result of a project to add journaling to XT2 with minimal impact. The migration for XT2 to XT3 is very easy, no backup and restore required, and it's possible to migrate in the reverse direction as well. The XT3 file system was integrated into the kernel version 2.4.15. JFS was developed at IBM, is integrated into so-and-so kernel. XFS was originally developed by Silicon Graphics in the early 90s. Is XFS still in the kernel? I think it is. No. BTRFS. FAT. Support for various file systems is enabled using kernel options that are set under the file system menu when configuring the kernel. At At the time of writing, work is in progress on 2 other file systems that provide journaling and a range of other advanced features. ext4 file system is its successor to ext3. The first pieces of the implementation were added to Linux kernel 2.6.19, and various features were added in later kernel versions. Among the planned or already implemented features of ext4 are extends, reservation of continuous blocks of storage, and other allocation features that aim to reduce file fragmentation, online file system defragmentation, faster file system checking, and support for nanosecond timestamps. BTRFS, BTreeFS, usually pronounced ButterFS, is a new file system designed from the ground up to provide a range of modern features, including extents, writable snapshots, which provide functionality equivalent to metadata and data journaling, checksums on data and metadata, online file system checking, online file system defragmentation, space-efficient packing of small files, space-efficient indexing, index directories. It was integrated into kernel version 2.6.29, single directory hierarchy, and mount points. On Linux, as on other Unix systems, all files from the file system reside under a single directory tree. At the base of this tree is the root directory / other file systems are mounted under the root directory and appear as subtrees within the overall hierarchy. The superuser uses a command of the following form to mount a file system: mount device directory. This command attaches the file system on the named device to the directory hierarchy at the specified directory, the file system's mount point. It's possible to change the location at which the file system is mounted. The file system is unmounted using the umount command and then mounted once more at a different point. With Linux 2.4.19 and later, things became more complicated. The kernel now supports per process mount namespaces. This means that each process potentially has its own set of file system mount points, and thus may see different single directory hierarchy from other processes. We explain this point further when we describe clone new ns flag in section 28.2.1. Oops. Still got a lot of stuff to go on file systems here. It's been 43 minutes so far. Wanted to get done with the exercises. I got 2 hours left. Okay, I think I can do that. To list the current mounted file systems, we can use the mount command with no arguments. As a following example, whose output has been somewhat abridged. Figure 14.4 shows a partial directory and file structure for systems on which the above mount command was performed. This diagram shows how the mount points map onto the directory hierarchy. So the pills are directories and the rectangles are files, regular files. SDA6 file system, SDA8, SDA9, SDA1. Cool. Mounting and unmounting file systems. The mount and unmount system calls allow a privileged cap sysadmin process to mount and unmount file systems. Most Unix implementations provide versions of these system calls. However, they are not standardized by SUSV3, and their operation varies across both Unix implementations and across file systems. Before looking at the system calls, it's useful. Mount and unmount. Yeah, it's useful to know about 3 files that contain information about the file systems that are currently mounted or can be mounted. A list of currently mounted file systems can be read from Linux specific proc mounts virtual file. Okay, cat proc So that's similar. If I do a word count on that versus if I just said mount, yeah, they're the same. Okay. Proc mounts is an interface to the kernel data structure, so it always contains accurate information about the mounted file systems. With the arrival of the per process mount namespace feature mentioned earlier, each process now has a proc PID mount. Cat proc, we'll say like what? Self mounts. Yeah. Cool. Proc PID mounts file that lists the mount points constituting the mount namespace, and proc mounts is just a symbolic link to proc self mounts. Okay. The mount and unmount commands commands automatically maintain the file etc mtab. Etc mtab, and isn't there fs tab? Yeah. Okay. Automatically maintain the file etc mtab, which contains information about that is similar to that in proc mounts, but slightly more detailed. In particular, etc mtab includes file system specific options given to mount, which are not shown in proc mounts. However, because the mount and umount system calls don't update etc mtab, this file may be inaccurate if some applications that mount or unmount devices fail to update it. The etc fs tab file, maintained manually by the system administrator, contains descriptions of all the available file systems on the system and is used by the mount and unmount, mount, umount, and fs check commands. The proc mounts, etc mtab, and etc fs tab files share a common format described in the fs tab manual page. Here's an example of a line from proc mounts file, which is device, mount location, file system type, options, and some numbers. Mount flag, sorry. A number used to control the operating of file system backups by dump. This field and the next are used only in the etc fs tab file. For proc mounts, used only in the etc fs tab file. For proc mounts and etc mtab, these fields are always 0. Number used to control the order which file system checks the file system at system boot time. The get fsent and get mntent manual pages document functions that can be used to read records from these files. Mounting a file system. Mount. The mount system call mounts a file system contained on a device specified by source under the directory, the mount point specified by target. The name source and target are used for the first two arguments because mount can perform other tasks than mounting a disk file system under a directory. Wait a minute, let me reread that. So we got mount, got a source and a target. Source is the device, target is the directory probably. And then we got the file system type, the mount flags, and we got some arbitrary data at the end. So the names source and target are used for the first two arguments because mount can perform other tasks than mounting a disk file system under a directory. The fs type argument is a string identifying the type of file system contained on the device. The mount flags argument is a bit mask constructed by ORing 0 or more of the flags shown in table 14.1. which are described in more detail below. The final mount argument data is appointed to a buffer of information whose interpretation depends on the file system. For most file system types, this argument is a string consisting of comma-separated option settings. A full list of these options can be found in the mount manual page for the documentation of the file system concerned if it's not described in mount 8. So mount flags, values for mount. Bind, create a bind mount. So we'll learn about bind mounts later. There is a section on advanced mount stuff. Create a directory named, dirsync, make directory updates synchronous. Mandlock, permit mandatory locking of files. Move, it's how it can move mount point to a new location. Okay, so you don't have to unmount and remount. No at time, don't update last access time for files. I guess that's a performance thing, probably. No dev, don't allow access to devices. No dir at time, don't update last access time for directories. No exec, don't allow programs to be executed. That's interesting. No SUID, disable set user ID and set group ID programs. Read only mount files can't be created or modified. Rec, recursive mount. Rela time, update last access time only if older than last modification time or last status change time. Remount with new mount flags and data. Strict A time, always update last access time. Synchronous, make all file and directory updates synchronous. Bet you that's has some performance overhead. The mount flag argument is a bit mask of flags that modify the operation of mount. Okay, we're going to talk about all these flags now. The mount flags argument is a bit mask of flags that modify the operation of mount. 0 or more of the following flags can't be specified in mount flags. MS bind, create a bind mount. We describe this feature in section so-and-so. If this flag is specified, then FS type and data arguments are ignored, as are the flags in mount flags other than MS rec, which is recursive mounting. MS dirsync, make directory updates synchronous. This is similar to the effect of open osync flag, but applies only to directory updates. The MS synchronous flag described below provides a superset of this functionality of MS dirsync, ensuring that both file and directory updates are performed synchronously. The MS dirsync flag allows the application to ensure that directory updates open, create, rename, link, unlink, symlink, and make dir are synchronized without incurring the expense of synchronizing all file updates. The FS dir sync FL. Why are these MS? These mount? But what is the S for? I don't know. Alright, the FS dir sync FL flag, section 15.5. Next chapter. I don't know why I'm hiccuping. Serves a similar purpose to MS dir sync, with the difference that FS dir sync FL can be applied to individual directories. In addition, on Linux, calling fsync on a file descriptor that refers to a directory provides a means of synchronizing directory updates on a per directory basis. This Linux-specific fsync behavior is not specified in SysV3. MS mandlock, permit mandatory record locking on files in this file system. We describe record locking in chapter 55. Good lord, it's way deep in the book. MS move, atomically move the existing mount point specified by source to a new location specified by target. This corresponds to the move option of mount. This is equivalent to unmounting the subtree and then remounting it at a different location, except that there's no point in time when the subtree is unmounted. The source argument should be a string specified as the target in a previous mount call. When this flag is specified, fs type and data arguments are ignored, as are the remaining flags in the mount flags. Okay. This is ridiculous. I never get hiccups like this. I'm gonna grab some water. Put some music on here.
In the beginning, there were 5 notes, 0, 4, 0, 9, 7, 16 notes in the scale of G minor. Subtract 1 octave. The sound was a sawtooth wave, tamed with acid. Visualize the lead. Next, kick drum, trance kick drum, 4 on the floor, with the scope. Increase the power by ducking our lead with the kick. Targets 3, 4, 5, 6. Next, bass. The sound should be a superstar.
That is Switch Angel. Really like her music. Alright, I'm gonna zoom in on her a little bit just in case people can't see that in the recording. I wonder if there's a way, can I get rid of this bar here? That's not. Yeah, let's do that. Where did we leave off? I think we read the move. So ms no add time. Don't update the last access time for the files in this file system. The purpose of this flag, as well as ms no dir add time flag below, is to eliminate the extra disk access required to update the file inode each time the file is accessed. In some applications, maintaining this timestamp is not critical, and avoiding doing so can significantly improve performance. The no add time flag serves a similar purpose to the fs no add time fl flag, with the difference that fs no add time fl can be applied to single files. Linux also provides similar functionality via the no add time open flag, which selects its behavior for individual open files. Whoa, what happened there? it scroll? Watch. Okay, didn't scroll that time. MS no dev. See? There's like a ghost in the machine here. It's not the first time it's happened. I don't know, something's glitchy. Don't allow access to block and character devices on this file system. This is a security feature designed to prevent users from doing things such as inserting a removable disk containing device special files that would allow arbitrary access to the system. No dir at time. Don't update the last access time for directories on this file system. This flag that provides a subset of the functionality of ms no at time, which prevents updates to the last access time for all file types. ms no exec. Don't allow programs or scripts to be executed from this. This is the one that I wasn't aware of. That is pretty cool. Is the no exec. Don't allow programs or scripts to be executed from this file system. This is useful if the file system contains non-Linux executables, or you just want to like provide a data volume that's read-only. You can do read-only no exec. ms no suid. Disable set user ID and set group ID programs on this file system. This is a security feature to prevent users from running set user ID and set group ID programs from removable devices. ms read-only. Mount the file system read-only so that no new files can be created and no existing files can be modified. ms rec. This flag is used in conjunction with other flags. ms bind to recursively apply the mount action to all the directory all of the mounts in a subtree. ms real time. Update the last access time for files on this file system only if the current setting of this time start ms real time. Update the last access time for the files on this file system only if the current setting of this timestamp is less than or equal to either of the last modification or the status of the or the last status change timestamp. This provides some of the performance benefits of ms no at time, but is useful for programs that need to know if a file has been read since it was last updated. Since Linux so-and-so, this behavior is provided by ms real time is the default, unless ms no at time flag is specified and the ms strict at time flag is required to obtain classical behavior. In addition, since Linux so-and-so, the last access timestamp is always updated if the current value is more than 24 hours in the past, even if the current value is more recent than the last modification and last status change timestamps. This is useful for certain system programs that monitor directories to see whether files have recently been accessed. ms remount. After the mount flags and data for the file system, alter the mount flags and data for the file system that is already mounted, e.g. to make a read-only file system writable. When using this flag, the target argument should be the same as for the original mount call, and the source and fs type arguments are ignored. This flag avoids the need to unmount and remount the disk, which may not be possible in some cases. For example, we can't unmount a file system if a process has files open on or its current working directory located within the file system. This will always be true of the root file system. Another example is where we need to use ms remount is with tempfs, memory-based file system, which can't be unmounted without losing their contents. Not all mount flags are modifiable. See mount 2 manual page for details. ms strict at time. Always update the last access timestamp when files on the file system are accessed. This is the default behavior since Linux 2630. If ms strict at time is specified, then ms no at time and ms rel at time are ignored if they are also specified in mount flags. ms synchronous. Make all file and directory updates on the file system synchronous. In the case of files, this is as though files were always opened with the open osync flag. Starting with kernel 2615, Linux provides 4 new mount flags to support the notion of shared subtrees. The new flags are MS Private, MS Shared, MS Slave, and MS Unbindable. These flags can be used in conjunction with MS Recursive to propagate their effects to all of the submounts under a mount subtree. Shared subtrees are designed for use with certain advanced file system features, such as per process mount namespaces. See the description of clone new NS in section 28.2.1 and the file system and user space facility. The shared subtree facility permits file system mounts to be propagated between mount namespaces in a controlled fashion. Details on shared subtrees can be found in the kernel code file system, subtree, and so and so. Example program. Oh god. So much file system stuff. I feel like pushing ahead right now. I'm like not really enjoying reading some of this stuff. I mean, most of this stuff I already knew. A lot of details I didn't know for sure. But just like broad highlights, I definitely knew most of this stuff. I never actually looked at the mount syscall, so it's nice to see its prototype and kind of like see some of the flags and like the remounting, the atomic move mount. The no exec. Yeah, I mean, like there's some cool stuff in there that I didn't know about. I'm curious if Michael, I'm going to take a little break here from reading. Michael Karisk. Is it Karisk like that? Like that. Okay. So I went to one of his training courses in 2019. It was about containers. Might have been around the time that he was doing this talk. No, it wasn't September. It would have been. Maybe it was September. I think it was more around August. But I think this is it. Containers Unplugged. I think he published all this stuff here. Yeah, this is all of his material that he went over in the courses. He printed it all out for us. He gave the lectures. And it seems like some of these lectures are recorded here. He's just so prolific. I couldn't imagine doing all this work. he is a prolific person. I mean, his work just like 2006. What's the copyright on this? Let's see. I mean, it says 2010, but I think the original publishing of this is earlier than 2010. Let's look for the Linux programming interface. Is there a Wikipedia? Is Wikipedia? Yeah, it was 2010. So he was giving talks and tutorials 2006. I was still in college in 2006. I graduated 2007. So he started his like kind of like tutorial and talk career way back here. And then he wrote and published the book 2010. Why kernel space sucks. I mean, just consuming all of his written material, tutorials, video lectures, consuming all of this stuff, you'd effectively have mastered Linux at that point. I mean, obviously Linux is so much bigger than any one person can like deal with, but as far as like knowing all the stuff you need, I would say that would be sufficient. All right. All right. Let's dive into. Oh, there's one other thing I wanted to look at. Training courses. So he does online prices. I mean, I've taken his courses before. He does online courses now. So for public 5-day online course, the per attendee price is 3,300 reduced to 3,200 booked. And I don't really like this format though, because I feel like reading and doing exercises based on what you're reading, and then maybe having some supplementary conversations with people. I feel like that is more effective to learning than for me than it just going into like a course, like a 5-day course, because it's so much content in a single week, and it's not go at your own pace. Like you're on the pace of the course, and everyone wants to go at their own pace. So it'd be too fast for some people, too slow for others. Like several times in reading this book so far, I mean, I'm not that far in. I'm probably like, I don't know, a good fifth way through. But several times in reading this, I'll just go on like a side tangent and just like play with something. And that isn't really like something that you could do when you're in the middle of a course. does a lot of writing for LWN too. Wow, this is insane. He is so prolific. I guess he stopped writing for LWN in 2014. Hey, that was last year. 15th print run of the Linux program interface. He's just posting every time he has a print run. Main 7 is now HPS enabled. That's nice. This is where I got my book, was a 10th print run. Because I got it from the course that I took in 2019. He hasn't posted much about his activities here. It's not in the past few years. The definitive work. Let's just pick a man page at random, like man to open. Let's see who wrote this. Don't they have the authors? I thought they had authors. Maybe do like man. What's one like mount? Authors. There we go. Write me a quick shell script that searches all the man pages for authors and then counts the frequency of each author as in how many man pages they are listed as authors in on. I'm gonna seriously doubt that they get this right first time. We'll just do it here. Clipper content is not available as inferred output type application XSH. change mod plus x on test.sh, and then just run it. That. Yeah, that's not gonna work. Oh, it didn't. Okay. Let's see if good old Gemini can do this. I give up. Man, F-Sync. Man. Yeah, whatever. I'm done. Done trying to figure that out. Alright. I think I'm done messing around here. Ready to go back to reading. Okay. The program in listing 14.1 provides a command level interface to the mount 2 system call. In effect, is a crude version of the mount 8 command. The following shell session log demonstrates the use of this program. We begin by creating a directory to be used as a mount point and mounting a file system. SU. Make dir test fs. Then we're going to say, hey, tmount exe2 bsd groups dev sda 12 test fs cat proc mounts grep sda2. You see it's there. Grep sda12 etsy mount tab. We find the preceding grep command produces no output because our program doesn't update the etsy m tab. We continue remounting the file system read-only. So we say, hey, we're going to now do our T mount dash F RR so and so cat out proc mount servo change. String RO in the display in the line displayed from proc mounts indicates is a read-only mount. Finally, we move the mount point to a new location within directory hierarchy. Move. Using mounts, sysmounts. Pretty self-explanatory. The umount system call unmounts a mounted file system. And you just give it the target. A target argument specifies the mount point of the file system to be unmounted. On Linux 2.2 and earlier, the file system can be identified in two ways, by the mount point or by the name of the device containing the file system. Since Linux kernel 2.4, Linux doesn't allow the latter possibility because a single file system can now be mounted at multiple locations, so that specifying a file system for target would be ambiguous. We explain this point in further detail in section 14.9.1. It's not possible to unmount a file system that is busy. That is, if there are open files on the file system, the process's current working directory is somewhere in the file system. Calling umount on a busy file system yields the error ebusy. The unmount2 system call is an extended version of unmount. Oh, there's two unmount. I didn't know that. Man syscalls mount. Oh, there's an explicit move mount too. Old umount. umount 2. Alright, what was it saying? The umount2 system call is an extended version of umount. It allows finer control over the unmount operation via the flags argument. Why is my mic not going up? Is my mic too far away? Test. Okay. Hopefully that's loud enough. Alright. So we have unmount2, give the target and have some flags that you can specify. This flags bitmask argument consists of 0 or more of the following values ORed together. Mount detach. Perform a lazy unmount. The mount point is marked so that no process can make new access to it, but processes that are already using it can continue to do so. The file system is actually unmounted when all processes cease using the mount. Mount expire. Mark the mount point as expired. If an initial unmount2 call is made specifically specifying this flag and the mount point is not busy, then the call fails with the error again, but the mount point is marked to expire. If the mount point is busy, then the call fails with the error ebusy, and the mount point is not marked to expire. The mount point remains expired as long as no process subsequently makes use of it. A second unmount2 call specifying mount expire will unmount an expired mount point. This provides a mechanism to unmount a file system that hasn't been used for some period of time. This flag can't be specified with mount detach or mount force. Mount force and unmount even if the device is busy. Pulling this option can cause data loss. Umount no follow. Don't dereference target if it's a symbolic link. This flag is designed for use in certain set user ID root programs that allow unprivileged users to perform unmounts in order to avoid the security problems that could occur if target is a symbolic link that is changed to point to a different location. Advanced mount features. We now look at a number of more advanced features that can be employed when mounting file systems. We demonstrate the use of most of these features using the mount 8 command. The same effects can also be accomplished from a program via calls to mount, mounting a file system and multiple mount points. In kernel versions before 2.4, the file system could be mounted only in a single mount point. From kernel 2.4 onward, a file system can be mounted at multiple locations within a single directory hierarchy. Because each of the mount points shows the same subtree, changes made via one mount point are visible through others, as demonstrated by the following shell session. So, switch to root, make tempfs, make demo, then we mount to both of them. You can see they're both mounted there. Then we touch tempfs my file, and we see that it shows up in demo. The output of the ls command shows that the change made to the first mount point testfs is visible to the second mount point demo. We present one example of why it is useful to mount a file system at multiple points when we describe bind mounts in section 14.9.4. It is because a device can be mounted at multiple points that the unmount system call can't take a device as its argument in Linux 2.4 and later. Stacking multiple mounts on the same mount point. In kernel versions before 2.4, mount point could only be used once. Since kernel 2.4, Linux allows multiple mounts to be stacked on a single mount point. Each new mount hides the directory subtree previously visible at the mount point. When the mount at the top of the stack is unmounted, the previous hidden mount becomes visible once more, as demonstrated by the following shell session. So we mount up SDA12 to testfs, then we touch a file in there, and then we mount up SDA13 to testfs, and then we grep, we see that the mounts both exist. One is a ext, one is a riser, and then we touch testfs new file. This is my file on testfs, and now we're putting a new file. And we only see new file, and then we unmount it, so it's kind of like popping the stack, and then we see the mount still exists for ext3 now, and then we ls and we see my file. One use of mount stacking is to stack a new mount on an existing mount point that is busy. Processes that hold file descriptors open, that are chrooted jailed, or that have current working directories within the old mount point continue to operate under that mount. But processes making new access to the mount point use the new mount. Combined with the mount detached unmount, this can provide a smooth migration off of a file system without needing to take the system into single user mode. We'll see another example of how stacking mounts is useful when we discuss the tempfs file system in section 14.10. Boop, boop, boo. Bam. Sorry, I was behind a page there. So much more stuff to read. Okay. Mount flags that are per mount options. In kernel versions before 2.4, there was a one-to-one correspondence between file system and mount points. Because this no longer holds in Linux 2.4 and later, some of the mount flags values described in section 14.8.1 can be set to a per mount basis, set on a per mount basis. These flags are msnoattime, msnodev, all the flags. The following shell session demonstrates the effect of msnoexec flag. So we get into root, we mount 12 into testfs, we then mount with the option no exec, that's the same location, and into demo. And then we cat out prac mounts, we see both of them there. We copy echo bin into testfs, and then we run testfs echo, and it works. And then we try doing demo echo, and it says permission denied. Bind mounts. Starting with kernel 2.4, Linux permits the creation of bind mounts. A bind mount created using the mount ms bind flag allows a directory or a file to be mounted at some other location in the file system hierarchy. Allows a directory or file to be mounted at some other location in the file system hierarchy. This results in a directory or file being visible in both locations. A bind mount is somewhat like a hard link. I was going to say it's kind of similar to hard link, but different in two respects. A bind mount can cross file system mount points and even chroot jails. It is possible to make a bind mount for a directory. We can create a bind mount from the shell using the --bind option and mount as shown in the following examples. In the first example, we bind mount a directory at another location and show that files created in one directory are visible at the other. So we su to root, we're in testfs, we make dir1 and we touch dir1x, then we make dir2 and then we bind mount dir1 to dir2, we ls dir2, we see x is in there, we touch dir2/y and ls d1, and we see xy. In the second example, we bind mount a file at another location and demonstrate that changes to the file via one mount are visible to the other mount. Alright. So we cat a bunch of stuff into F1, then we touch F2, and we bind mount F1 to F2, and then we mount and grep for D1 and F1. Why D1? Is that because of the old directory? Yeah, okay. And then we cat out, or we cat a bunch of stuff to append onto F2. And then we cat F1 and we see that it shows up there. And then we rm F2. RM says, hey, I can't unlink F2 because it's not something that you're allowed to unlink. So then we, even though we're sudo, says you cannot unlink F2 because it's busy. So we unmount F2, and then we can rm F2. One example of one we might use, I'm going to play around with that just for 1 second here. mkdir test, just going to go into there. And we got touch F1 and F2, and if I echo hello world into F1, cat out F1, it's like that. And then if I sudo mount, actually I'm going to try it without sudo. Mount bind F1 to F2. Yeah, I have to sudo that. Okay. And if I ls here, so now if I cat F2 and cat F1, and if I vim up F2 and say, yo, my man, and cat out F1, has everything. So now if I do mount and grep for F1, no? No, just list all mounts. Shouldn't it show up there? F1? grep for bind. Maybe it just made it a hard link because it's on the same file system. Oops. Damn it. I think when I ran bind, it just created a hard link. Yeah, I could do a stat on this thing. Stat on F1, stat on F2. And the inode is the same. I think it just did a hard link. RM F2. No, it's treating it like a mount. Let's try asking it again. I created a bind mount between two files, two normal, or I say regular files. Give it the command. How do I tell if this mount exists? Oh, cat proc self mount info or mounts. Grep for bind. Mount info. There it is. Grep bind. No. It's under here. Shared. BTRFS. Yeah, it shows up there. Find mount F2. Find mount F1. Yeah. Find mount temp. Why doesn't this show as a bind mount and instead just says shared? Okay, whatever. I found it. So I can't RM F2, but I can U mount F2 sudo. And then if I cat out F1, 2, and now I can RM F1, F2. DR test. Okay. I just wanted to play with that a little bit. His output actually said that they're bind mounts here, but mine, I guess maybe because he's using BTRFS, didn't show that. Okay. One example of when we might use a bind mount is in the creation of a chroot jail. Rather than replacing various standard directories such as lib in the jail, we can simply create bind mounts for those directories within the jail. Recursive bind mounts. By default, if we create a bind mount for a directory using msbind, then only that directory is mounted in the new location. If there are any submounts under the source directory, they are not replicated on the mount targets. Linux 2.4.11 added the ms recursive flag, which can be ORed with msbind as part of the flag's argument to mount, so that mounts are replicated under the mount target. This is referred to as a recursive bind mount. The mount 8 command provides the rbind option to achieve the same effect from the shell as shown in the following shell session. Boop. Okay. All right, the end is near. I actually like bind mounts. They're pretty cool. We begin by creating a directory tree source 1 mounted under top. This tree includes a submount source 2 at top sub. Okay, so we get into root, we make dir top, make dir source 1, touch source 1a, mount bind source 1 to top, make dir top sub. Okay, this is getting kind of confusing. So we make dir top, make dir source 1, touch source 1 AA, and then we mount bind source 1 to top. So now top, I just made, oh, mkdr top, sorry. And now if I ls top or if I ls source 1, they're both the same. And then I make dir top sub and make dir source 2 and touch source 2 BBB, and then mount sudo mount bind source 2 into top sub, and if we run find on top, we got all of that. Okay, now we create another bind mount dir 1 using top as a source. Since this new mount is non-recursive, the submounts are not replicated. So we then make dir 1, and we mount bind top dir 1 sudo, and this should have nothing in it. I guess maybe the dir 1's AAA? No, because if we ls-la top, it might get the AAA. I think it will. Yeah. Oh, and it gets a sub, but there's nothing in there. Whereas top sub has the BBB. Okay. So if we find, or we do LT top and LT dir 1. And then if we mkdr dir 2, and then we mount rbind top dir 2, since it's an rbind, we'll get everything. And I have to sudo this. And then I'll do LT on dir 2, and I get everything. Cool. rmr dir 2 does not work, so I have to say unmount, or umount dir 2 sudo. Dir 2 is busy, so I have to go into, but dir 1 I can do without, yeah. But dir 2, because it's recursive, I have to do dir 2 sub first, and then I can do dir 2. And then I can rm dir dir 1 and dir 2. And then over here, I'm gonna mount top slash, LT top, sudo umount top sub, just top, rmdr top, rmdr source 1 and source 2. There we go. Oh. Yeah. That's right. Okay. Just unwind all that. presence of dir2 sub bb is the output of fine shows that the submount was replicated. A virtual memory file system, tempfs. All the file systems we have described so far in this chapter reside on disks. However, Linux also supports the notion of a virtual file system that reside in memory. To applications, these look just like any other file system. The same operations, open, read, write, link, makedir, and so on, can be applied to files and directories in such file systems. There is, however, one important difference. File operations are much faster since no disk access is involved. Boop. Next page. Various memory-based file systems. I could use some extra light here. Is that better? A little bit better. All right, various memory-based file systems have been developed for Linux. The most sophisticated of these to date is the tempfs file system. Sophisticated, well, which first appeared in Linux 2.4. The tempfs file system differs from other memory-based file systems in that it is a virtual memory file system. This means that tempfs uses not only RAM but also the swap space. So it's a virtual file system that uses virtual memory. So it's a virtual file system. Although the tempfs file system described here is Linux specific, most Unix implementations provide some form of memory-based file system. The tempfs file system is an optional Linux kernel component that is configured via the conf tempfs option. To create a tempfs system, we use a command of the following form: mount t tempfs source target. The source can be any name. Its only significance is that it appears in the proc mounts and is displayed by the mounts and df commands. As usual, target is the mount point for the file system. Note that it is not necessary to use mkfs to create a file system first, because the kernel automatically binds a file system as part of the mount system call. As an example of the use of tempfs, we can employ mount stacking, so we don't need to care if temp is already in use, and create a tempfs file system mounted on temp as follows. So we can mount type tempfs on top of temp. So we would have to say, so if I ls-la under temp, and I do word count line, there's 27 files in there. If I do sudo mount type is tempfs, new temp under temp, and then I do my word count, there's 0. And if I cat proc mounts, I get all that. If I say mount, I get that. And I'm gonna say, hey, sudo umount temp, and now when I do my ls, it's back to 27. Cool. A command such as the above or an equivalent entry in etc tab is sometimes used to improve the performance of applications, e.g. compilers that make heavy use of temp directory for creating temporary files. By default, the tempfs file system is permitted to grow to half the size of RAM, but the size equals n bytes mount option can be used to set a different ceiling for the file system size, either when the file system is created or during a later remount. A tempfs file system consumes only as much memory and swap space as is currently required for the files it holds. If we unmount a tempfs file system or the system crashes, then all data in the file system is lost, hence the name tempfs. Aside from the use of user applications, tempfs file systems also serve two special purposes. An invisible tempfs file system mounted internally by the kernel is used for implementing systemv shared memory, a shared anonymous memory mapping, and shared anonymous memory mapping. A tempfs file system is mounted at dev shm, run shm on some systems, is used for the glibc implementation of POSIX shared memory and POSIX semaphores. Boop. Obtaining information about a file system, stat VFS, system call, and fstat VFS. Stat VFS and fstat VFS library call functions Obtain information about a mounted file system. So these are library functions, not system calls. The only difference between these two functions is how the file system is identified. For stat VFS, we use a path name to specify the name of any file in the file system. For stat VFS, we specify an open file descriptor FD, referring to any file in the file system. Both functions return stat VFS structure containing information about these file system in the buffer pointed to by stat VFS buff. This structure has the following form. So we got, what we got here? We got block size, FR size. Amount of blocks, be free, number of free blocks, blocks available, files, free inodes, available inodes, file system ID, flags, and name max. The purpose of most of the fields in stat VFS structure is made clear in comments above. We note a new further point regarding some fields. The FS BLK count T and FS FILC and TT data types are integer types specified in susv3. For most Linux file systems, the values of FB size and FR size are the same. However, some file systems support the notion of block fragments, which can be used to allocate a smaller unit of storage at the end of the file if a full block is not required. This avoids a waste of space that would otherwise occur if a full block was allocated. On such file systems, FR size is the size of a fragment and FB size is the size of a whole block. The notion of fragments in Unix file systems first appeared in early 1980s. Blah, blah, blah. Alright, many native Unix and Linux file systems support the notion of reserving a certain portion of the blocks of a file system for the super user, so that if file system fills up, the super user can still log into the system and do some work to resolve the problem. If there are reserved blocks in the file system, then the difference in values of the FB free and FB available fields in the stat VFS structure tells us how many blocks are reserved. The F flag field is a bit mass of the flags used to mount the file system. That is, it contains information similar to the mount flags argument given to mount. However, the constants used for the bits in this field have names starting with ST instead of MS used for mount flags. susv3 requires only the ST read-only and ST no SUID constants, but the glibc implementation supports a full range of constants with names corresponding to the MS constants described for the mount flags argument. The FSID field is used to return a unique identifier for the file system, for example, a value based on the identifier of the device on which the file system resides. On older Linux kernels, many types of file systems return 0 in this field. susv3 specifies both stat VFS and fstat VFS. On Linux, as on several other Unix implementations, these functions are layered on top of the quite similar statfs and fstatfs system calls. Okay, so they are system calls. Some Unix implementations provide a statfs system call, but don't provide stat VFS. The principal difference, aside from some differently named fields, are as follows. I might be coming down with something. My coach mentioned this morning that all of his clients came down with something. I'm feeling like crap. And I felt like crap over the weekend too, with like congestion and stuff. I might just be fighting off like a cold right now. All this congestion and sneezing. I've been sneezing constantly. So I guess I should prepare for getting sick. Usually when your coach is sick, or any of his clients, or most of his clients are sick, chances are you're going to get sick. Yeah, I can feel my body temperature going up too. It's not good. Alright, well, almost done with this chapter, so principal differences, aside from some other differences, differently named fields are as follows. The stat VFS and fstat VFS functions return the flag field, giving information about the file system mount flags. glib implementation obtains this information by scanning proc mounts or etc mount mtab. The statsfs and fstatfs system calls return the field ftype given the type of the file system, e.g. the value so-and-so indicates that this is the ext2 file system. The file system subdirectory in the source code distribution of this book contains two files, t-stat-vfs and t-stat-fs, containing .c demonstrating the use of stat-vfs and stat-fs. Okay. Yeah, I'm like, my nose is running now. Yep. Devices are represented by entries in the dev directory. This is a summary. Each device has a corresponding device driver, which implements a standard set of operations, including those corresponding to the open, read, write, and close system calls. A device may be real, meaning that there are corresponding hardware device, or virtual, meaning that there's no hardware device exists. But the kernel nevertheless provides a device driver that implements an API that is the same as a real device. A hard disk is divided into one or more partitions, each of which may contain a file system. A file system is an organized collection of regular files and directories. Linux implements a wide variety of file systems, including the traditional ext2 file system. The ext2 file system is conceptually similar to early Unix file systems, consisting of a boot block, a super block, an inode table, and a data area containing file data blocks. Each file has an entry in the file system's inode table. This entry contains various information about the file, including its type, size, link count, ownership, permissions, timestamps, and pointers to file data blocks. Linux provides a range of journaling file systems, including RISE-0FS, ext3, ext4, XFS, JFS, and BDRFS. The journaling file system records metadata updates and optionally on some file systems data updates to a log file before the actual file updates are performed. This means that in the event of a system crash, the log file can be replayed to quickly restore the file system to a consistent state. The key benefit of journaling file systems is that they avoid the lengthy file system consistency checks required by conventional Unix file systems after a system crash. All file systems on a Linux system are mounted under a single directory tree with the directory / as its root. The location at which the file system is mounted in the directory tree is called a mount point or target. A privileged process can mount and unmount a file system using the mount and unmount system calls. Information about mounting file systems can be retrieved by stat-vfs. I want to go back to this binding stuff because I feel like I want to highlight that as like something that I might want to do a video on. Further information. For detailed information about devices and device drivers, see so-and-so, especially so-and-so. Some useful information about device can be found in the kernel source and documentation devices. Several books provide further information about file systems. Tannenbaum is a general introduction to file system structures and implementation, provides an introduction to the implementation of Unix file systems, originally file system oriented, primarily towards System V, and also describe the System V file system implementation and describe the Linux VFS implementation. Documentation on various file systems can be found in the kernel source subdirectory. Documentation file systems. Individual websites can be found describing most of the file system implementations available on Linux. Exercise. Write a program that measures the time required to create and then remove a large number of 1-byte files in a single directory. I'm going to skip this one. I read this before. It seems just like another performance thing. All right. Chapter 15, it is 4:19. If we go back to my to-do list, I didn't do file system exercises. So maybe here we say start on 15. Bam. This is file attributes. This is like the file and IO desert that I've been walking in here the past few chapters. I appreciate like it's logical to have like all this like co-located in the book, but reading it like straight through is just so overwhelming, the amount of file and file related stuff. So we had file IO buffering. I guess they had file IO originally in chapter 4 or 5, and they broke it up with a bunch of other stuff. But then they go into file IO buffering, file systems, file attributes, extended attributes, access control lists, directories and links, monitoring file events. So we have to get to chapter 20 before we start getting into something new here. Which is signals. All right. Let's go in. So we're going to start reading file attributes, but before I do that, I'm going to say, oops. Let's keep that open there. Let's go over here. Clear, get status, LTN20 dot, not N, L, sorry. L like that, right? Okay, there's nothing here. Chapter 14. Oh, we did get status here. Get status. Yeah, there's nothing there. Get status. Vim readme. Chapter 15 is on file. Oops. Attributes. Okay. And then T, we'll say T7 done. So we are 21% complete. That means we're officially 1/5 of the way done with this book. Look at that, 1/5. It's going to be a long haul. What's today's date? It is 13th. Damn, we're already like 13 days into the year. I started this over the New Year week because I had a power outage and I just wanted to read something. And I was like, I'm going to read this whole thing. Because I've always wanted to do it and I have the time to do it. But now that I'm 1/5 done and I have 4/5 remaining, I feel like it's going to take forever. So say this is a half month. Then if at this rate that I'm going at, it would be what? Mid-March that I'd finish. I think if I like today, I had 3 sessions, or so far I've had 2 sessions of reading, and I'll have a third after I get done with my cardio tonight. So at the rate at which I was reading today, 2 chapters a day, and there's how many remaining? 50? That's 25 days. If I did that every day, I could finish potentially mid-February. So we're looking at like mid to late February for me to finish this. Which is insane because I'm reading, like today I read a lot. I did 2 chapters, I did experiments, I played with different examples. I did one exercise that took a while on chapter 13. I mean, I'm not doing crazy stuff like I was doing before, but yeah. All right, we got 30 minutes remaining, so let's start on file attributes, and then I'll need to run to the store, do some grocery shopping, eat dinner, and then get back, do some cardio, at least 30 minutes. So I might not have but more than like an hour. I think I might just take a break now. That way I can go to the grocery store, get all my stuff done, and then come back. So it's gonna be at least an hour and a half, maybe 2 hours. So 4:30, 5:30, 6:30. So I'll probably be back around 6:30 my time. If not earlier, if I can get this stuff done faster. Let's go ahead and push, and then I'll go to github.com. Oh yeah, I forgot how to open PR against Marchi. I mean, that's quite a lot of progress. I mean, it's reading this book, I feel, is like great because it's fleshing out a lot of details for things that I just haven't had the time or curiosity to explore on my own. Or I had like a slight curiosity and questions about something, but have never really fully explored that. And so this is just giving me all that information up front. It's like, here's everything. The problem is that there is a lot of information here that I kind of don't really feel like I need. Like just looking through like what I've accomplished so far, like users and groups, like I always wondered what the semantics of groups were in relation to permissions. And like basically what I learned in reading this chapter is that syscalls do not consider groups for authorization. It's like file system operations. The set UID and set GID stuff, I was a little bit iffy on. Like I touched on that back in 2019 when I did that course with Michael Karisk. Like he touched on the set GID and set UID, but obviously I didn't really like commit that to memory. I didn't really know where those bits were stored at. The other thing I really appreciated was, I think it was in this chapter here, or maybe this one. He like laid out the relation of file descriptors to the file description to the inode, which I never saw like a very clear kind of diagram showing the relationship. It's like I guess that you would say it's a many to many. Many to many, would that be the right phrase? Between all of them? No. It would be a many to one relationship between file descriptors and file description, because you can have many file descriptors pointing at one file descriptor, but it's not the reverse. You can't have more than one file description for a single file descriptor, if that makes sense. So it's a many to one, and then between file description and inode, I think that would be a many to many. No, I think that's the other way, which would be an inode can be pointed to by multiple file descriptions, but a file description points to one inode. So I think it's a many to one and then a many one. Anyways, I really appreciated having the time to kind of like review that model and where different flags are set. And the close exec flag is on the file descriptor, and it's the only flag that's on the file descriptor, whereas all the other flags are on the file description, including the offset. So when you're seeking, if you have the same file description between two different file descriptors, then you have shared offset. Whereas if you have two different file descriptions for the same inode, you could be doing IO on the same data in the same file, but have different offsets that you seek to. So lots of stuff. There's so much stuff. The memory allocation, like having a good handle on memory allocation. Like I feel like I have a better memory model of like how memory is managed now. I never even thought about like the API of malloc and free. Like it's just like, okay, you malloc, you get a pointer back, and then you give that pointer to free, and it frees the memory. It's like, yeah, but how does free know how big of a block of memory you have? You're not passing explicit size to free. So glibc actually encodes the size of that block of memory in the byte before the pointer. Like stuff like that is just like, I just never really thought about, you know? And how it does allocations to reduce the amount of memory used at the, I guess you would say, higher memory addresses of the heap. And as a result, you know, if a certain amount of memory is freed or is available at the top of the heap, then it'll call break to like lower the amount of memory used by that process. And that's all the responsibility of the memory allocator. And the fact that I could not easily, but I mean, it's not too hard to implement a memory allocator doing something like that, like your own memory allocation API. Like the only syscall is break, the BRK, or sbreak or whatever it is. But like that's the only syscall that all these memory allocators are using to control the size of the heap. And then all their algorithms and techniques for like dividing up the memory inside of that heap is all just implementation detail. And you can have your own API. Like you don't have to use malloc and free. Like that's just a libc thing, you know. And it's got to be curious. It's got to be curious about like how is libc actually implement malloc and free. I could see myself diving into that at some point now, because all it is implementation detail. I know how at the end of the day it's like going down to break syscalls. So it might be something I do in the future, like look into how libc's memory allocation works. Yeah, it's just like so much stuff to process credentials. Jesus Christ. Time? Yeah, I guess time I felt I had a pretty good grasp on already. But yeah, 2 chapters now in file IO or file systems, file IO buffering, file stuff. I think I got 3 more remaining. So, all right, get through this. But yeah, I'll take a break here for dinner, and I will be back in about 2 hours to continue reading on chapter 15. Cool.